out the recurrence first, and then you will have to build this transition matrix. So typically this matrix, I mean this smaller matrix which you are considering, here we only need Fn and Fn minus 1. So we are considering these two elements only. If that particular recurrence is dependent on 10 variables, then you will have to consider all 10 of them, and note that in the next step you need Fn plus 1 also, I mean the next element also, but whatever other dependencies which you have considered, you have to consider them also in this matrix basically. So you will have to consider all those basically. So if it's dependent on say 2, 3, I mean the second last element and the third last element, so probably you will have to consider the 1 also, because 2, 3 would lead to 4, but from 3 you need to calculate 4 also and 2 also, so you need 1 also there. So n minus 3, n minus 2, then we are saying this, right? So we need 2 also and 3 also. Okay, and when we reach, we'll be calculating 4, right? For that we are calculating F5. Suppose we are calculating F5, then we need F3 and F2, right? Sorry? Yeah, just I'm explaining that. So if we, next step we'll be requiring F6, right? So we'll be requiring F5 and F4 and F3. So we need to have this F4. So while this transition we need to calculate F4 as well. So we'll have to include that F4 also. I mean, we can't work with F2 and F3 only. This we have to figure out at that moment that what all is necessary. Sometimes it will be redundant. Now how to calculate matrix power n? We've already discussed that, I guess, in that is logarithmic exponentiation. We can, for n, what we can do is we can m raised power n is equal to m square to the power of n by 2. If n is even, and you can take another case of even and odd, and according to that you can calculate the exponentiation in logarithmic time. So typically the complexity would be the size of the matrix. If size of the matrix is n, then n cube matrix multiplication into log of the power which you are trying to calculate. Typically in this particular case the matrix is really small, so we ignore this and say that the order to calculate this number is log p. There is another way to do the Fibonacci number problem, that's the golden ratio problem. There is a closed form formula for that, but then that formula is like not integer formula, it has 1 plus root 5, something like that. So due to the computer we can't, I mean this will result in floating point errors and won't give the accurate value for that. And if you start raising to a very high power, then this error will grow, I mean even more. So when to use this? Whenever there is a linear recurrence, you are given to calculate something like 10 raised power 9th element, 10 raised power 8th element of very high value. You can't follow the linear pattern, so you can guess that probably that problem would break into a linear recurrence. It might look on the first go that's a quadratic, or it's not a, it's a non-linear recurrence, but then you can figure out, I mean that's a logical part of the problem. Break it into this particular linear recurrence and then you can solve it. So now I'll be covering another problem which is like number of paths of length k in a graph. So you need to give me report the number of paths of length k such that even the vertices can repeat. So a path from 1 to 2 to 3 to 1 to 5 is also a valid path basically. One is repeating, it's not the shortest path. We are calculating all the possible paths, even the vertices can repeat. How can we accomplish that? Sorry? Edges?
Can the edges repeat?
Yeah, everything can repeat.
Take the adjacency matrix power k.
Yeah.
And ij entry of that be the number of paths from I to j using k.
So what he just suggested is right. You just need to calculate the kth power of the adjacency matrix, and the A of ij will denote the number of paths from I to j. Now why it works I'll explain. So consider this matrix. When this is V1, V2, V3. Just I'm showing the multiplication. So what will be the multiplication? You multiply this row with this column. So V1 to V1. This will denote that okay, I stay at V1. So it will be 1. This particular multiplication V2. This is like this particular thing denotes that there is an edge from V1 to V1. This is V1 to V2. So if I am considering this particular edge, so I can go from V1 to V2 in 0 ways. Similarly for V3. So likewise I will be writing these terms. So from Vij we can go to so the number of ways from traveling from I to j would be choosing any middle vertex k. We consider all the paths from I to k and from all the paths from k to j. So what we will do, we will choose any one path from I to k, any one of them, and any one of the paths from k to j. The total number of paths for reaching from I to j would be I to k into k to j. No, k would be the summation. So basically when we are multiplying this matrix, we are this is I, j, and this particular k we are selecting. So we are moving in this, right? So we are each time we are considering one middle vertex and going via that. Let's move on to another problem, which looks to be a counting problem. So you need to report all the strings of length n such that the string ACM doesn't appear in that. You are given the standard 26 letter English alphabet set, and you need to report all the strings of length n such that a particular string like ACM doesn't appear in that. As a substring.
Find the number of strings where it appears.
How will you find the number of strings where it appears? So there is no string. See, the problem I'll clarify. You have n boxes, n length string. You can create any. You can choose A, B, C, D, anything you want. Okay, so there is no question of KMP. You need to report how many strings will be there. And that can be extended to a set of words also, or which should contain some words and which should not contain some words. Let's assume we are looking for the string of length I, all the strings of length I which doesn't contain ACM till now. So there will be three cases. Either it ends with A, or it's ending with a letter AC, or it's ending with a letter, some other letter. Is that clear? Because it won't end with ACM, because we are considering I length strings in which ACM doesn't appear. So it will fall in either of these cases. So we can write a recurrence for this. So what will be f of A? I plus 1. F of A I plus 1 would be nothing but f of A I, because if the previous character was A also, I'll choose next character as A, then my ending will be A only. or FAC of I choose A, it would be like ending with ACA, which is equivalent as ending as A. And even if it's ending with some other character, then also I choose A, then also it's fine. Is the recurrence for FA I plus 1 clear? Now we'll calculate it for AC. To end up with AC, the previous character should be A. So it would be directly equal to F of A of I. And similarly, for ending with some other character, so if the previous character was A, then this character could take either, it cannot take A, otherwise it will fall in the category of ending with A. It cannot take C because otherwise it ends up in AC. So there are 24 choices for this particular thing. So 24 into F of A of I. If it ends with C, then it cannot take A. There are other 25 possibilities valid for, yeah, there are other 25 valid. So it's 25. So it cannot have M. If we are considering FAC, it cannot, M we cannot choose because then we'll be completing ACM. So again there are 24 possibilities if we are considering AC. And if we are considering some other, then there are 25 possibilities. Now this is the recurrence, simple recurrence. So what you can do is you can form the transition matrix for this. It's fairly simple to do, and you can then do the matrix exponentiation to find out the answer. Another one thing which I missed was that suppose you are asked to find the sum of all Fibonacci numbers till n. I mean sum of all linear recurrence till n. So something like sum f1 plus f2 plus f3 and so on till n terms. So again you can see that this sum is also following a linear recurrence, that sum of I will be equal to sum of I minus 1 plus f of n, f of I. So again in the matrix transformation you can include this term. So this particular term after the multiplication will give the sum, and the other nth term is also calculated in the same go. You don't need to calculate it separately. So you can try out for exercise the problem. I'll just post the code. I'm not very sure that there are two problems on spot on that I took a case where only one particular string should not appear. There's a problem when a particular set of strings should not appear. So in that case you will have to basically, I mean just 3 states. There will be much more states in that, and you will have to create that transition matrix for that, and after that you can simply end up doing matrix exponentiation and solve it. You can try out the problems. PL hop, PL hop is fairly simple. A lines, live game, okay, we move on to the last technique, which is like can be useful sometimes. Is like, suppose, I mean we are given the problem, we know the transition matrix already, and like the test cases for the problem are like very much high. They are like 60,000 or 70,000, of the order of 60,000 or something. Matrix is fairly small. These are 60,000 and test cases. We have reduced the problem to this matrix exponentiation problem. Then we know that we end up in log of p multiplications. Basically log of p matrix multiplication will be needing to solve each case, and if say p is like of the order of 2 power 64